Okay, so this is the second part of a video that we started, but we just kind of ran out of time, ran out of room. But we'll continue on. So we're basically going to use these formulas that we talked about in the previous video to do a particular problem. So let's scroll down and do this problem. So this one, so let's bring it to the top. So this one says if I add 45 grams of sodium chloride to 500 grams of water, what will the melting and boiling points, boiling, so this is misspelled, there should be an I in there, not boiling, but boiling, but anyhow, and boiling points be of the resulting solution, okay? So let's go ahead and look at uh, the boiling point first. Let's do the boiling aspect first. So our formula for um, the change in temperature, delta T, so it's delta T B is equal to KB. Let me make that a little neater. So KB times molality times my Van't Hoff factor of I. So remember, this is a lowercase cursive I. So let's go ahead. So because we want to find what the new boiling point is, we have to find out what our change in temperature is going to be. So I'm just going to continue to write this down. Delta TB is equal to, now K was a constant. So the constant of water, because this is the particular solvent that we're using, okay, so each solvent has a different constant, but because we're using water, the particular boiling constant for water is point or 0.51, and the units on the K is degrees Celsius per molal. Okay, so we'll go ahead and put that into parentheses because we're going to be multiplying here. So the next thing that we have to figure out is the molality. Okay, so if you'll recall, molality, and I'll do this down here, molality was equal to moles of solute divided by kilograms of solvent. So if we look up here, we've got 45 grams of sodium. So we know that we can get moles out of grams. All we have to do is use the molar mass. I won't actually write that work out. I just hope that by this point in the game you guys can go from 45 grams into moles. But anyhow, after we convert using our molar mass, 45 grams of sodium chloride is actually going to give us 0.77 moles. So I'll continue this over here. So 0.77 moles of NaCl. So once again, I didn't show the work here, but 0.77 moles is equivalent to 45 grams. So I just converted the 45 grams into moles using the molar mass of sodium chloride. So the kilograms, we have 500 grams of water, but this is in unit of grams. We do not want grams because kilograms is in the problem. So in order to convert 500 grams to kilograms, the decimal is understood to be at the right of the last zero. So just move the decimal 1, 2, 3 spaces to the left, and then that's going to give us 0.500 kilograms of water. So now once I take my 0.77 and I divide by 0.5 kilograms, my molality is going to be 1.54, and I'm just going to put a little lowercase m beside it to remind us the m here, but this is actually the unit, so 1.54 molal. That's such a fun word to say, molal. But anyhow, so now that we've got what our molality is, this number, the 1.54, goes into our formula here. So I'm going to go ahead and continue writing on. So I'm going to say 1.54 molal. Okay. Now the next thing I have to worry about is this I. So I'm going to look at what I'm dissolving, what my solute is. So let's switch to another color here. So let's do this kind of magenta purple looking color. So sodium chloride. So if I were to write this out, sodium chloride is NaCl. But I have to figure out, is this ionic or covalent? Well, I know right off the bat that this is ionic because sodium is a metal. Anytime you have a metal mixed with a nonmetal, it's going to be ionic. So when sodium chloride goes into solution, it will form sodium plus 1 ions. Let's make it a little better. Sodium plus 1 ions, and it will make chlorine negative 1. So it makes 1 sodium, it makes 1 chlorine, so 1 and 1 gives me 2. So I've got a Van't Hoff factor of 2, so I'm going to put 2 in for there. Now there are no units on the 2. This is actually termed a dimensionless number, so there are no units, so we don't have to worry about that. But if you'll look here, the molality cancels out with the other molality here, and the unit that I'm left with is the degrees Celsius. So let's bring this on down here. So my delta TB is going to be, when I multiply 0.51 times 1.54 times 2, my change in temperature is actually 5.7288. And the units on that is degrees Celsius. So I'm almost done. I'm not done quite yet because this is my change in temperature of the boiling point. So this is just telling me how much I'm changing it. If we go to the question is asking what is the boiling point. So it's not asking what the change is, it's asking what is the new boiling point. Well, we know that water normally boils at 100 degrees Celsius. And if I am elevating the boiling point, meaning I'm increasing the boiling point by 5.7 degrees Celsius, all I have to do is take 100 degrees Celsius and add it to my delta T. So 5.7288 degrees Celsius. So my final answer is going to be 100 and, oh, let's see here. Hang on. I think I may have made a mistake. Okay, yes indeed, I have made a mistake. And here's my mistake. So going back, if I take 0.51 times 1.54 times 2, I do not get 5.7288. So let's grab a different color here. Let's get rid of this because that's not correct. Okay, so let's go back to my green. Decrease my brush size. Okay, so now when I multiply 0.51 times 1.54 times 2, the answer that I actually get for that is 1.571, and it's still degrees Celsius. So now let's go back and get rid of this, the 5.7, because that's what I got. So let's get rid of that. Okay. So now we're good. So it's basically the same reasoning. So this is my delta TB. So 1.571 is my change in temperature. So if I'm elevating it, I'm increasing the boiling point by 1.571 degrees Celsius. It normally boils at 100, so we're going to add 100 to 1.571 degrees Celsius, and my final answer is going to be 101.57 degrees Celsius. This is going to be my new boiling point, okay? Because my delta T, this is how much it changed, and if it normally is 100, I just add my change to the 100, and this is my new boiling point. So now let's figure out, or calculate rather, what the melting point is. So if you guys will remember from phase change diagrams that mathematically speaking, the melting point is the same as the freezing point. So freezing and melting mathematically are the same thing. It basically just depends upon which phase you're starting with and whether you're adding heat or taking heat away. But mathematically they are the same thing. Or numerically they are the same number. So let's switch colors and we'll go ahead and put our formula for the freezing point depression down. So that's going to be delta TF is equal to Kf times molality times the Van't Hoff factor. So delta TF, so it looks just like the formula we had for boiling, except for, like we said, the subscripts, the F's and B's are a little different, but the formula is generally the same. So for this particular instance, though, the Kf, the freezing constant for water, we're still dissolved in water, so that number actually changes, but it is a constant. It is not the 0.51, but the Kf for water actually turns out to be 1.86, and the units are degrees Celsius per mole. Now, once again, this is not a number I would expect you to remember. it will be in a chart that you'll typically have on a test or quiz. The molality, we've already calculated the molality to be 1.54. That's not going to change because we still, if we go back up to the problem, we still have 45 grams in the same solvent, the same solution. So the molality is not going to change. So we're going to keep the same molality that we had. So I'm going to go ahead and put in for molality the same thing, which was 1.54 molal. And the Van't Hoff factor, because it was still sodium chloride, that's not going to change either. So the Van't Hoff factor is 2. So when we multiply all of these numbers out, we're going to find our change in freezing point. So when we take 1.86 times 1.54 times 2, now we get the 5.7288. This was the number that I had written previously up here that was incorrect. I looked at my answers differently. But anyhow, this is correct for the freezing, the delta TF. So this is degrees Celsius. So now once again, the question is not asking for what is the change in freezing point. It's asking what is the melting point. So we know that the freezing point, now once again, freezing and melting, same thing numerically. I'm just going to use the terminology freezing because we've got our subscripts F. For water, water normally freezes at 0 degrees Celsius. But because this is freezing point depression, and you depress something means you make it lower, so we are actually 5.7288 degrees lower than we normally are at 0. So this is going to be 0 minus 5.7288 degrees Celsius. Yes, and this is a 5. So once we do that, our answer is going to be negative 5.7, and I'll round to 3 here, degrees Celsius. So this is our new freezing point or melting point, however you want to say it.